Hi everyone, and welcome to our second TIA Centre seminar of the academic year. So my name is Adam Shepherd, and I'm a researcher here at the TIA Centre. And today I'm absolutely delighted um, to have Dr. Rohan Chakraborty from UCL and the Alan Turing Institute join us. I'm also pleased to announce today for the TIA Centre seminar series that I've now got a co-host, Chachi, who's going to be helping host and run and organize these seminars. If you want to quickly say hello, Chachi.
I just turned my camera on. Yeah,
Yeah, that's fine.
Yeah, my pleasure to be joining the organization of the TI seminars, and hopefully I will take on more of these seminars in the future.
Fantastic. Thanks, Chachi. So back to Rohan. So Rohan is a theme or group lead in Frontier AI Assurance at the Alan Turing Institute and a principal research fellow at UCL Cancer Institute. He leads TRAIL, the transparent and responsible AI lab shared between UCL and Turing. Rohan is an invited expert in responsible AI with the global partnership on AI and an editor with Springer Nature Computer Science. Rohan has a PhD in computer science and worked as a postdoctoral researcher at the University of Oxford, where he continues to an honorary fellow of Lincoln College and lecturer in computer science with Christ Church College. And the title of Rohan's talk today is Conformal Quantification of Predictive Uncertainty in Health AI. And Rohan, we're very much looking forward to your talk. So with that, I'll pass over to you. Thank you very much.
Thank you. Yeah, so I'm Rohan. I lead the TRAIL lab, which is shared between UCL and Turing, as you just heard. There are two main work streams in TRAIL, which is the transparent AI work stream and reliable AI. I will cover one half of the work we are doing now, which is the reliable AI part. So, but just to give you an idea of the overall work package that we are following now, within the transparent AI workstream, the type of models we are currently interested in are concept bottleneck models. And within that, we particularly want to solve certain mathematical problems or grand challenges within that area, which is leakage of concepts. So when you're doing concept learning with concept bottlenecks, sometimes there is some information leakage between the concepts, which sort of destroys the effect of interpretability altogether. And if you're interested in that work package, which is led by my postdoc Enrico, I can share a paper with you later, which is under review in JMLR, Journal of Machine Learning Research. But we are not looking at that today. We are looking at the other work stream, which is the reliable AI work stream, which is led by my other postdoc mentioned here, Ariane. There, what we are interested in is, can we give guaranteed quantification of uncertainty of predictive models using conformal prediction? This is the part we will go into more details today. And Fiona is the third postdoc in the group, and she is an engineer, and she sort of implements the models hands-on. Enrico is a physicist, mathematician. Ariane is a statistician, mathematician. Right. So that's the type of work we do. Where AI assurance comes in, which is my position at the Turing, is you will see that how these two methods of explainability are slightly different from the stuff out there, is that these methods can give a notion of guaranteed explainability by design. Conformal prediction is an example of that, and we will come into that now, how it gives a guarantee. So can concept bottlenecks, by the way. Right. So I have around 24 slides or something, half of which is setting up the maths behind it. And then around 12 slides of 3 or 4 examples of papers from my lab with applications in healthcare. So today's talk, by the way, just to point out, has nothing to do with tissue image analysis or cancer imaging in particular. However, conformal prediction for uncertainty quantification is a generalized statistical framework. So essentially, you can use it as an additional layer of analysis in almost any projects that you are doing at the moment. So it has quite broad applicability. Okay. So what is the ultimate goal? What we are trying to say here is we want to quantify uncertainty using a set for classification tasks or intervals for regression tasks that are likely to contain the true prediction. But one could also do that with confidence intervals. What's the difference here? It's likely to contain the true prediction with a certain percentage of guarantee. And that guarantee is, we ensure that guarantee with something called a calibration phase, which we will go into. So here it might be best to sort of differentiate the uncertainty as is usually done in statistics, which is aleatoric versus epistemic. The aleatoric uncertainty are mostly the uncertainty which is inherent in the data with the model parameters fixed, and the epistemic uncertainty is more the other way around, where the data is fixed and the parameters are modeled at random. What we are interested here actually is the predictive uncertainty. So another advantage of conformal prediction is that it is actually model independent. So it can be used for any AI model that you are using for the predictive task, but it is a calibration-based approach to quantify the uncertainty in the prediction. Right. So what do we mean by the coverage guarantee or conformal coverage guarantee? What we mean is, if you have a predictive model here, probability of y given x. Now, something to really note here and to be completely clear about is that when we are saying probability y given x here, for doing the conformal calibration, the training is already done. So the model is already trained. We have kept, so just like usually in machine learning tasks, we keep a training set, we may have a validation set, and we have a test set. These are held out, right? So that is, these are unseen by each other, but it is assumed that they belong to the same probability distribution. Here, what you need to have is one additional holdout set called the calibration set. Now, in that calibration set, you have the examples xi, yi, which are the inputs and outputs. So we are talking about the calibration phase here. The training is already done. Now, given that collection for calibration, xi, yi, suppose you have a new test sample xn plus 1. So this is a sample from the test set. We want to create a confidence set. So at the moment, we are talking about the classification task. We want to create a confidence set cx plus n plus 1, which belongs to the total number of labels which are out there. So suppose we have a 10 class classification, so k would be 10. Within those 10 labels, we want to create a confidence set, also called the conformal set, for this new test sample xn plus 1, such that we can say that the true level is in that set above a certain level of confidence. So that's where the 1 minus alpha is coming in. So given a user specified level of guarantee needed for this particular task, depends on what the task is, given the alpha, what is the conformal set for this particular test sample, such that we can be sure that the true level is included in it above 1 minus alpha. Now, this is interesting because several reasons. Firstly, this means that if the test sample is really challenging, the number of items that will end up in your conformal set, that number itself will increase so as to reach that 1 minus alpha level for that particular sample. That means you almost have a personalized quantification of uncertainty. And the length of your conformal set that you have at the end is itself a reflection of how challenging that test sample is, and what's the uncertainty involved. In addition, okay, we will come back to the guarantee itself. So the guarantee is called marginal, not personalized. So the calibration set is personalized. So for each sample, you will have a calibration set, a conformal set at the output. But the guarantee given is marginal. We will come back to that. Marginal or population level, not personalized. Anyways, there are some examples at the bottom. The true class for each is underlined, is underlined. So for the first one, you just have one entry in the example, in the conformal set, and that is correct. So it has high confidence and it is correct. And as you go down the row, you will see that there are a couple of examples where there are several items in the conformal set. None of them are correct. So it is uncertain and it is wrong. Or it can be that it needs to have several items in the conformal set so that the true class is included. That's the final one. Okay. Now there are a couple of things here which are assumptions here, quite strong assumptions, and people are working on these, including my team, on relaxing these assumptions. So the first sort of assumption for conformal prediction, and it is one of the only assumptions actually, which is exchangeability. That is, the conformal set and your test set belong to the, have the same distribution. Now, that seems like a very strong assumption, and it is, but then we often make this assumption in machine learning anyways, that your training set and test set have the same distribution. Of course, this immediately fails when you have a continual learning type of scenario with population drift or population shift. Then this exchangeability criterion will not hold. And how to use conformal prediction in those situations, there is a lot of research going on there. But in sort of vanilla, like basic conformal prediction, this is the main assumption. Having said that, exchangeability is actually a weaker assumption than the IID assumption, that is, they are independent. And often we make that IID assumption in machine learning as well. So it is a strong assumption, but it is not uncommon to make anyways. So it's not something very special to conformal prediction. So this is not an assumption, but this was the other point I was noting, which is the conformal guarantee, the coverage guarantee is marginal or population level. So that is because you are ensuring the guarantee through that calibration phase with the calibration set. So of course, that is based on the whole set. So it is not individualized. But then again, having said that, you do get the calibration, the conformal set for each sample. So at least from the length of the set, you get an idea of individualized uncertainty. But the guarantee is not individualized. So conformal prediction with thresholding. So how do you actually do the conformal calculation? So the basic implementation of conformal is actually quite simple, especially for the multi-class classification scenario. If you are interested to have a sort of quick training in conformal prediction, I would suggest looking at this really nice handbook called A Gentle Introduction to Conformal Prediction. It is as the name suggests. And it has like code snippets along with it. I think it's available on archive. It's 50 pages long, but if you go through the first 10 pages, you will be well on your way. So anyway, so if you have, for a given alpha, what you need to find is a threshold tau such that for any class for which your test sample has a higher prediction than tau, that can be just your softmax, say, in a deep learning framework, you include that class in your conformal set. Now, how to get the tau? This is the formula, which is you have alpha, and if you have n as the number of samples in your calibration set, then tau is alpha by n plus 1 quantile. There is a proof of this. You can go through it. It's included in the handbook as well. So so it's really easy to implement, but then you get this conformal guarantee, marginal guarantee, that your true class will be included over the sample space at that level of alpha. Another way of looking at this is what is called the p-value approach. Because essentially you are saying that this is often used in the anomaly detection scenario. Essentially what you are saying is, given an alpha, is your sample close enough to your calibration distribution, or it is too different? If it is close enough, it gets included in the conformal set. So that's the p-value approach to it, often used in anomaly detection scenarios, but it's converges to the same thing. Right. As I said, the conformal guarantee is marginal or population level. However, we might be using conformal prediction, say, as a metric for AI fairness, where I want to see whether the uncertainty quantification is same across certain patient subgroups with respect to, say, age or gender or ethnicity. Then what we would want is to have that coverage guarantee for each of those groupings. Now, split conditional says that, of course, if you have enough samples, it depends on how large your data set is, you could, and if you have a notion of what the subgroups should be, you can sort of pre-divide the data set as well as the calibration set as well into those groups. And if you have enough samples in each of them, you could do the same conformal procedure for each of the subgroups you are interested in. And that's split conditional. However, there is a special case of split conditional called class conditional. So what is class conditional? Now, suppose you are doing cancer subtyping and or cancer grading, and you have a certain number of classes, certain number of grades, or certain number of subtypes. Those are your output classes. And at the same time, you are doing split conditional on certain patient subgroups, say with respect to gender. So that's the usual split conditional. However, it can be that you want to do split conditional, that is, have the coverage guarantee across the class levels themselves. That is, if you have a certain number of subtypes, you want the conformal guarantee across those subtypes. So if the class levels and your conformal splits are the same, it's called class conditional coverage. Now, the previous examples had to do with classification. You can also use conformal prediction for regression. It would be similar here. The prediction level, again, it can be some sort of like regression predictive output. It would need to be above that threshold tau. And the tau you can again get from the alpha by n plus 1 quantile formula. But instead of it becoming a conformal set, that is, it is included in the set if it is above tau for a certain class, here it would be a range from minus tau to plus tau. So in case of conformal regression, the tau ends up providing a conformal bound. That's the difference. Right. So I think we have covered very like a whistle stop tour of the underlying concepts and the main terminology. Now we will go into the healthcare application part through 3 or 4, I think 4 papers from my lab, recent papers. Now, how these 4 have been chosen, because you will find more conformal prediction related papers in my publication list. I have chosen these 4 so that one is an example for classification, one is for regression, and the third one is for generation. In fact, the first conformal prediction paper on generative imaging, so generative AI for medical imaging, was from the Trail Lab a few months back. So that's the third paper. And then there is a 4th paper which brings everything together. So we will go through each of these very quickly. So, and you can look up the details and ask me questions later. So, right. So this is the first of them. This is the classification situation where we are taking the very sort of established and well-known example of skin lesion classification. It's not new at all. But we wanted to show that how to use conformal prediction in this situation, and how to use it also as an additional metric of performance, but also metric of fairness. So, as I said, what AI model you are using for the prediction doesn't really matter in this situation. It can be any. What you want to do is, if you have, say, 7 or 8 type of skin lesions, you would want to first do some sort of class balancing, train the AI model, and then after the AI model is trained, you use the calibration set, which you have held out separately, to find the tau, the threshold. And then for the test samples, as each of them come in, for all the classes among those 8 classes, you have a prediction above tau. Those classes will be included in the conformal set for that test sample. That's really it. I mean, it's quite simple. So this is exactly just what I said right now. But then you can use that as a metric of uncertainty across your um, uh, uh, patient subgroupings or splits. You can use a normal conformal and just look at it post hoc. Or you could, if you have enough samples, you could also do a split conformal as well, as we have seen before. But more interestingly, you could use the conformal scores if you are doing several iterations of training. You could, after each iteration, or you can even do it epoch-wise, you could use this conformal scores as an additional cost function or error value as well to optimize over different iterations of training or over epochs. So it can be an additional error term as well, in addition to any cross-class error term that you are trying to minimize for higher accuracy. The second paper is on conformal prediction for cuffless blood pressure prediction. Again, it is deliberately chosen like a very simple, well, not simple, but well-known problem. And there are many papers out there. Deliberately chosen like that because we wanted to show how conformal prediction works in that scenario. So that other people can start to use it. So there is a little bit of advocacy as well, because we are trying to popularize conformal prediction. In fact, we are making a claim that the paradigm of machine learning training, which has been established so far, which is training, testing, and sometimes validation, needs to have this additional calibration set as well. Anyways, so conformal prediction here for cuffless blood pressure, of course, it's a regression task here. So it will be a conformal bound or range instead of a conformal set. So this was a project collaboration with Microsoft Beijing, who had this data set, which is they have oscillographic blood pressure, which is with cuff. So that is the ground truth. And you have cuffless sort of indirect monitoring with wearable devices. And you have some model, some predictive model, again, doesn't really matter for conformal, which has been trained. And then having trained it, you use the calibration set to find, again, the tau, and use the tau to give this kind of range that we see in this figure here. So basically, you are getting a bound. Now, why is the bound important? It is important because you are monitoring this with wearable devices. So you can do one of two things with the data you are collecting. You can just collect it and for some clinical experts to analyze offline. Or you could provide some sort of reading of the blood pressure to the patient. But now you would want to do that because you have the smartwatch or whatever. But that makes it quite a risky proposition, because you want to be careful that the patient doesn't take a wrong decision based on what you are displaying there. So that's why this kind of uncertainty quantification, in this case, it's not a fairness question, it is more of a safety question. So this data set was quite rich and had all of this different attributes to it that can be used in interesting ways for conformal prediction. These are the equations how to get to it. So essentially what you have here, we should start with this step. I don't know whether you can see my cursor. We should start with this step and work backwards. So what you are seeing here essentially is this minus q hat or plus q hat, which are the two sort of bounds. That bound you are getting from this value s, which is a function of your essentially it's called the conformal score. The conformal score is a function of your probabilistic prediction. So conformal score for classification would be a function of your softmax. And what that function would be dictated such that it falls between these 1 minus alpha and 1 minus alpha plus 1 by n plus 1, which is that 1 by n plus 1 quantile we were talking about earlier. Okay, conformal prediction for generation. So this is the third paper. Now, we wanted to show, so the origin of this work was that if you are using generative AI, language-based, say large language models to generate poetry, or imaging generative AI to generate, say, AI art, for the same input and for the same trained model. So for the same input and for different instantiations of the model, you would probably want a little bit of variation to keep it interesting in case of AI poetry or art. So the variation or uncertainty in that case is not a problem. It is not a bug, might be a feature. In case of healthcare, though, if you think of the input for a particular patient, when you are generating the output for the same model in different instantiations of the model, it is weird if the output changes. In this case, it's an imaging example. So what can be imaging examples for generative AI? It can be image super resolution, as in this case. It could be cross-modal generation of different types of radiology, etc. Super resolution is the most, is the least there is some debate in cross-modal image generation for medicine, whether it should be relied on or not. But super resolution, basically image enhancement, is the more safer example. So we took that because the formulation of conformal would be the same for the two. So what we want to do here is, what we did here is that there would be some variation if you are using, say, a diffusion-based model, because due to the stochasticity which is inherent in the model. It can be mitigated or controlled. It's difficult to make it zero. However, if we accept that there will be some variation, can we quantify the variation? Quantify the variation using conformal prediction with some guarantee. So what you basically do is you have the low resolution image, you have a trained model which provides high resolution image, you have a calibration set for that model. For each image, you generate maybe a certain number of images, and for whatever number of images you have in your calibration set, you have that many times, right? You use that set to do your calibration. You find the tau. Interestingly, conformal prediction generation is very much alike the regression case, because you would have a sort of bound. What you want to do is, for the user, say a radiologist, you not only want to give the super resolved image, but you can give a bound within which it would lie. And within that bound, you can also sample. That is, you can provide a few examples of output to the clinician for the human expert to take the final decision, guaranteeing that those are sampled from that plus minus tau range. So that was the main point of this paper. Adding one thing to that is, of course, when we are getting the initial data set, we are getting radiology samples at a certain resolution. We don't really have the low resolution and high resolution at that point. So what we did for this is actually we took those incoming samples as for the training phase as our high resolution samples. We downgraded them and which yielded the low resolution samples for training. So the default samples during training are treated as high resolution. Their downgrading counterparts are the inputs during training. Once the training is done, the model is basically a super resolving model, such that if new samples come in at the original resolution, it now generates a super resolved version of that, if that makes sense. Again, the exact model doesn't really matter for this talk because we are focusing on the conformal part. Now, if you look at this, again, if we start from this last set of equations and work backwards, it is almost same as the regression scenario. So you have this minus and plus, which are basically your tau, your two upper and lower bounds. The alpha, so alpha hat times G rays, which is UX, is your conformal score, as I said earlier. The alpha hat comes from a weightage of your the weightage of the significance value alpha, the weightage coming from n, which is the size of your calibration set. So it's exactly similar with little bit of modifications. Of course, there will be some modifications because you are applying it in a different scenario. But other than that, the underlying steps are not difficult if you just go through. I will share the link after the talk. Okay. So then this is the latest paper, which sort of brings everything together in a multimodal cancer scenario. This might be more aligned to some of the work happening at the TIA Center. So here we have the generative part, which is generating transcriptomic signatures, cancer transcriptomic signatures from H&E images. And also there is a multimodal prediction part, which is partly classification, that is grading and subtyping, and partly regression, that is prognosis, survival risk score. Using, again, like benchmark data set, TCGA. So several cohorts of TCGA. Now you will see there are several papers out there which does this kind of stuff, that is predicting grade, risk from multimodal cancer data. There are several from just Mahmood Lab alone. What those don't have is this conformal angle. So we have used conformal in this paper on the generative side, the regression classification all together in one paper. And this was recently accepted in Nature Comms. It is not online yet, but the preprint is online. I think it is this, this QR code should lead there. I can also share later, or you can find on my Google Scholar. So the code is also available on GitHub, publicly available, and you can, it includes the conformal implementations of all the parts as well. So this is my last slide. A little bit about the Turing work, which is more like generating impact or leadership. which is so some of the AI work packages of what is called the India-UK Vision 2035 is being led through the Turing. I obviously am from India, so I'm leading this from the Turing side. A good part of that is what we call the AI Assurance Toolkit, which the Turing was tasked to develop by the UK government anyways, I mean, separate to the India-UK Vision. Now these two are coming together in the sense that we want to promote conformal prediction as a way of doing AI assurance. On the sort of reliability of decision end. Now, explainability of model end, that's where the concept bottleneck stuff comes in, but that would be part of a separate talk. And these are some perspective papers from my Turing group, recent papers which have been published. Okay, that's it for today. Thank you.
Fantastic. Thank you very much, Rohan, for a really, really great talk. I know we've only got a couple of minutes before you need to go. So with that, we'll open the floor to questions. Does anyone either online or in person have any questions that they'd like to ask Rohan? Yeah, of course.
Hi, Rohan. Good to see you again.
Hi, Faiz.
Yeah, would have been nice if you were here. But moving on to the question, I think some of the work that you presented is really impressive, and especially related to the cancer. I think we need a separate talk on that once the paper is published, definitely. So congratulations on that. But my question to you is about: have you seen uses of conformal prediction in language model generation, like text generation, and
Good point. So
what does the problem even mean? Help me understand that.
yeah. So right. So I am firstly not an expert in LLMs, but I would like to expand my current conformal formulations to LLMs, specifically in the cancer scenario. So the work that we are doing now, again, the background work is, there are a couple of papers out there, which is in TCG, as you know, Fires, you have the digital pathology images and some pathology reports, right? So you could train a model, like a VLM model, vision to language, which is generating that report. In fact, you would come across a couple of papers which is already doing that. What we want to do is start from there and use conformal prediction for those, for the language output. Now, your question, what does it mean in that case, doing conformal prediction? Okay, by the way, I can tell you what it would mean in my, as it is in my vision at the moment. How to do it, I don't know the answer yet because I'm trying to do it now. So, so what we would like to have is those pathology reports might have a part which is structured and might have a part which is free flowing, like a free text, unstructured, right? So if we have enough examples in the calibration set, and we use those examples in the calibration sets as ground truths and make sure that the output does not go beyond a certain threshold, a certain bound of uncertainty. Now, what does it mean in the case of language? I don't know completely yet. This project is with Microsoft Research Cambridge. They also don't know exactly what's the answer, but that is what we want to do in the project that we are working on right now, actually. So with a couple of students, but whether we are successful or not, I think you will get to know in a few months' time. Okay. That's the project we are working on now. Yeah.
Thank you.
Brilliant. Thank you, Rohan. Do you have any final questions that there's an
while we wait for a question, maybe I can share a couple of links that people would find helpful. Firstly, if anyone is interested in reading up a bit more on this, because this is so generalized, whatever projects you are working on, you can add it as long as it is some classification or regression scenario. So maybe first is, I will just share quickly 2 or 3 links. The first link is this one, which is the Gentle Introduction to Conformal Prediction. It's like a handbook. It has a very nice introduction with some code snippets, etc. After reading this, if someone gets obsessed with conformal prediction like I am, the follow-up reading would be this one by the same person, same author. I will just share that one as well, but that is this one is like quite theoretical, so that would be a additional reading sort of. Okay, and
Yes.
and maybe I should share this multimodal cancer paper with conformal that I just mentioned. And that would be, just give me a second. Right, it is this one. So if you look at the abstract, you will see the GitHub link is also there. So the third link is the Nature Comms paper that got accepted recently. That should be enough for now. I might, because this one is slightly different, I will also share one last one, which is the so this fourth one is the paper which is on the image generation. So I'm adding that because it's slightly different from the others. So conformal prediction for image generation. That's about it. Before I go, may I plug? So if Fayaz is still there, Fayaz, I wish I could be there in person today. The meeting, the person you should blame is your colleague Deepak Parashar, because he and I are organizing this event, which is from 3. If you or anyone else in this call want to join it online, so the other way around, feel free to join this event, which starts in 10 minutes.
What is the event about?
So the event, so the speaker is the head of the biostats unit at University of Michigan, Professor Veera, I'm forgetting his surname. So Veera is going to present his work, which is multimodal cancer. So it is again has to do some statistical analysis, I will get to know as well, but of digital pathology, clinical genomics, etc. So it would be quite aligned, at least topically. But if someone is free, welcome to join online. So it is this registration link that I just shared.
Thank you. Brilliant. Thank you very much, Rohan. Really
Thank
appreciate
you.
it.
Okay, I will go and set up the stuff. Yeah.
Yeah, I hope the meeting goes well. Thank you very much, Rohan.
Thank you for having me. See you. Bye.
See you. Thanks everyone online.